Ever wondered how movies and video games make surfaces look so real? Like the way light dances across a metallic car or the subtle glow of a fabric. It all starts with something called material modeling. But here's the thing. Creating digital materials that behave like real ones is a huge challenge. Traditional methods rely on massive datasets of light reflections, but they're clunky and hard to tweak. Enter FreNBRDF, a groundbreaking approach that uses math and AI to make digital materials more realistic, flexible, and easier to work with. Let's break it down. Imagine you're trying to recreate a material's appearance from scratch. You need to capture how light interacts with its surface, every angle, every shimmer. That's what BRDFs, bidirectional reflectance distribution functions, do, but they're like giant databases of data. Too big for most practical uses. Neural networks offered a better way, encoding material properties into compact models. But there was a problem. These models did see the frequency of light interactions. Think of it like trying to paint a sunset with only a few brushstrokes, missing the subtle gradients that make it look real. That's where FreNBRDF shines. The researchers used a mathematical tool called spherical harmonics. Think of it as a way to break down complex light patterns into simpler, structured components. By integrating this into their neural model, they taught the AI to understand the frequency of light reflections, not just their raw values. Here's how it works. The model first converts material data into a continuous function, like mapping a 3D surface to a mathematical formula. Then spherical harmonics analyze this function, extracting frequency-based clues about how light scatters. These clues become a new loss function, a kind of training guide that helps the neural network refine its predictions. The result? Materials that look more natural, with smoother transitions and better detail. Testing showed FreNBRDF outperforms existing methods. It reconstructs materials faster, edits them more intuitively, and even handles tricky cases like highly reflective or anisotropic surfaces. Imagine tweaking a car's paint job in real time, or creating virtual textures that react to light like real fabrics. This isn't just about better graphics, it's about making digital worlds feel more alive. So the next time you're dazzled by a lifelike scene in a game or movie, remember, behind the magic is a blend of math, AI, and clever problem solving. FreNBRDF is just one step in a journey to make the digital and physical worlds blur together, and that's pretty amazing. Thanks for watching. If you want to dive deeper into how AI is reshaping computer graphics, hit subscribe. Until next time, keep exploring. Hey everyone, welcome back. Today we're diving into a fascinating breakthrough in computer graphics, something that's making materials in virtual worlds look way more realistic. Meet FreNBRDF, a new method that's redefining how we reconstruct and edit material properties. Let's break down what makes this research so exciting. So imagine you're creating a video game or a virtual reality experience. The materials, like the texture of a wooden table or the shine of a metal surface, need to look just right. But how do you teach a computer to replicate those subtle details? That's where FreNBRDF comes in. It's a neural network that learns the language of materials, allowing it to reconstruct and even modify them with incredible accuracy. Now, how did the researchers test this? They used a dataset of 30 real-world materials called MERL, which are like digital twins of physical surfaces. The process? They split their data into training, validation, and testing sets. Think of it as practice, feedback, and a final exam. They trained their model using an optimizer called Atom, which helps the network learn by adjusting its parameters. At each step, they tracked losses, like errors, and tweaked settings to get the best results. But how do you measure if a material looks realistic? The team used 3 key metrics. 1. RMSE, root mean squared error. This measures how similar the reconstructed material is to the real 1 pixel by pixel. Lower values are better. 2. PSNR, peak signal-to-noise ratio. Think of this as a clarity score. Higher values mean the image is sharper and closer to the original. 3. SSIM, structural similarity index. This checks how perceptually similar the 2 images are to the human eye. Again, higher is better. And there's also this special frequency rectified loss, a clever trick to ensure the material looks good not just in detail, but across different scales. It's like making sure a texture looks natural, whether you're zoomed in or out. The results? FreNBRDF crushed the competition. When compared to 2 state-of-the-art methods, it outperformed them across all metrics. For example, while other models struggled with consistency, FreNBRDF maintained high-quality reconstructions, even when blending materials. Imagine smoothly transitioning from a shiny chrome surface to a rough stone texture. FreNBRDF does this with precision. But here's the real kicker. FreNBRDF doesn't just reconstruct materials, it edits them. By working in a low-dimensional space of neural representations, the model can interpolate between materials, creating seamless transitions. Think of it like mixing paint, except the computer does it automatically, producing lifelike results. What's next for this tech? The researchers hope to apply it to more complex materials, like those found in real-world physics. Imagine games or simulations where every surface feels authentic, or virtual environments that respond to light and touch just like the real world. Let's dive into the tools and ideas that made FreNBRDF possible. To reconstruct those 30 complex materials with such detail, the researchers didn't just rely on guesswork. They used cutting-edge techniques from computer graphics, machine learning, and math. First, they tackled a big challenge: how to accurately model how light interacts with surfaces. This is where BRDFs, bidirectional reflectance distribution functions, come in. Think of them as a material's fingerprint for light, how it bounces off in different directions. But traditional methods struggled to capture this efficiently. But how do you teach a computer to understand these complex patterns? That's where DeepSets stepped in. This approach lets neural networks process unordered data, like a list of light interactions, without worrying about the order. It's like teaching a kid to count blocks, no matter how they're stacked. This flexibility was key for handling the messy, real-world data the team worked with. Then there's the magic of spherical Fourier neural operators. Imagine a neural network that can learn patterns on a sphere, like mapping the Earth's weather. By applying this to light interactions, the team could model how materials behave from every angle, creating super realistic results. It's like giving the computer a 360-degree view of a material's personality. Of course, training such a system needed the right tools. They used atom optimization, a smart algorithm that adjusts settings on the fly, like a personal trainer for neural networks. And to make sure their reconstructions were visually spot-on, they relied on structural similarity metrics, which compare images the way our eyes do. It's not just about numbers, it's about making sure the final result looks right to us. Putting it all together, these techniques let FreNBRDF achieve something amazing: high-fidelity material reconstructions that outperform older methods. It's a testament to how combining clever math, adaptive learning, and human-like perception checks can push the boundaries of what's possible in digital creation. Thanks for watching. If you want to dive deeper into how AI is reshaping computer graphics, hit subscribe. Until next time, keep exploring.